Good day, everyone. So we are reviewing Wetzel's Limnology textbook. This is edition number 4, and we are starting today on chapter 10, Water as a Chemical Environment, with Louis A. Mollott, with the Faculty of Environmental and Urban Change, York University in Toronto, Ontario, Canada, and Peter J. Dillon, with the School of the Environment, Trent University, Peterborough, Ontario, Canada. So let's get started. Water as a solvent. An aquatic ecosystem is as much a chemical environment as it is a physical one. Because of its very high polarity, water is a solvent capable of dissolving an extraordinarily large number of substances. These include metabolically essential substances as well as harmful substances. Solubility is influenced by numerous factors such as solute, chemical structure, as well as environmental conditions, including temperature, pH, and oxidation potential. Non-polar compounds are characterized by very low solubility. Known to illustrate the importance of chemical structure to solubility, compare the non-polar aromatic ring benzene with the solubility in water of 1.8 grams per liter at room temperature to a slightly different C6 compound or carbon-6 compound, phenol, with a solubility of 8.3 grams per liter. Substitution of an H plus for a hydroxide group, so H plus being a proton or hydronium, for an OH minus, which is hydroxide group, increases the ring's polarity slightly and its molar solubility over threefold. Another C6 molecule, glucose, is much more polar and has a solubility of 909 grams per liter. Water as a solvent not only provides a medium from which aquatic organisms can acquire substances, but also brings into contact solutes that may chemically react to produce new substances while lowering reactant concentrations. This means that ecosystem productivity and ecological structure are profoundly dependent on a substance's capacity for dissolving in water and factors which remove and add it to solution. Solubility is to be distinguished from the actual concentration of a solute, which is often less than maximum, in which case it is said to be undersaturated. Solute concentration is affected by rates of input from sources external to lakes, discharge downstream, adsorption to particulate matter, chemical reactions that use or produce the solute, precipitation after reacting with other solutes, degassing and microbial assimilation, excretion, and decomposition. These rates can vary significantly over time and space. This chapter begins with a brief summary of the basic principles governing chemical reaction and then examines factors that affect solute concentrations. For the purposes of this chapter, two categories of solutes are recognized. One, substances with a solid phase within temperature and pressure ranges found in lakes, such as major nutrients, trace metals, major ions, and organic compounds. And two, gases, such as carbon dioxide, oxygen, nitrogen, hydrogen sulfide, and nitrous oxide. There is some overlap between these categories. For example, metals are often bound to organic carbon and ammonia, especially above pH 9, and elemental mercury are volatile, vaporizes readily. 2. Chemical reactions in freshwater. The 5 major classes of reaction that occur in freshwaters are acid-base reaction, most of which involves proton or H+, redox reactions that involve the transfer of electrons, and photochemical reactions involving free radical productions via the breaking of covalent bonds by photons to produce chemical species with single free electrons. Complexation reactions involving weak bonding between dissolved molecules or atoms, and adsorption-desorption reactions, which involve the interaction of solutes with solids. Acid-base reactions. An acid-base reaction, or Bronsted-Lowry definition, is a chemical reaction that involves an exchange of one or more hydrogen ions between between molecules that may be neutral or electrically charged. So what is interesting here is, like, we're talking about hydrogen ions, H+, and we're also talking about protons, H+ here, and there's also another definition of it, which is hydronium. So in any case, I think probably we should just keep up just one terminology, maybe just a proton. That probably would work. In the Lewis theory of acid-base reaction, an acid is any substance such as a proton that can accept a pair of non-bonding electrons. Meanwhile, a base is any substance such as hydroxide that can donate a pair of non-bonding electrons. Carbonic acid, H2CO3, produced through the dissolution of carbon dioxide in water, is the predominant acid in most unpolluted fresh waters. It is also the source of many of the inorganic solutes in water through interaction with the lake or river catchment soils and rock. Dissolution of sedimentary substrate by carbonic acid provides high levels of base cations as well as bicarbonate ions, leading to waters with high ionic strength, while the interaction of carbonic acid with crystalline siliceous substrates provides the same cation but in much lesser amount. Low ionic strength waters with much lower bicarbonate concentration results. The carbonic acid bicarbonate-carbonate system is the dominant buffering system in natural waters, leading to pH values generally in the circumneutral range between 6 and 8.0. The presence of high levels of organic acids resulting from the decay of vegetative material can in some cases lower the pH significantly, while high primary productivity can alter the carbonic acid bicarbonate-carbonate equilibrium to favor carbonate, raising the pH to well above 9. Excessive inputs of anthropogenic acids, sulfuric acid, nitric acid, can also drastically lower the pH by overwhelming the buffering capacity of the water. The carbonate system is discussed in more detail in chapters 12 and 13. Redox reaction. Redox reaction. A redox reaction consists of two parts or half reactions: an oxidation reaction, in which a substance loses or donates electrons, which is coupled to a reduction reaction in which a substance gains or accepts electrons. An oxidation reaction and a reduction reaction must always be coupled because free electrons cannot exist in solution and electron must be conserved. Although these reactions may involve the transfer of oxygen, other substances may replace oxygen as electron acceptor. One of the most important oxidation reactions in natural waters is photosynthesis. CO2 plus water, carbon dioxide and water is, in this example, CO2 is reduced while water is oxidized. The converse reaction, respiration of organic matter, can be represented as CH2O plus oxygen is equal to carbon dioxide plus water, which is the sum of two half reactions. CH2O plus H2O is equal to CO2 plus 4 protons plus 4 electrons. When free oxygen gas is not present in the water, a situation typically found in the hypolimnia of productive waters, other electron acceptors, including nitrate, ferric iron, and sulfate, may replace the role of oxygen. So 2 nitrates plus 12 protons plus 10 electrons is equal to nitrogen gas plus 6 waters, which is denitrification. And then here is FeOOH plus 3 proton plus electron is equal, and then here sulfate with 10 electron and 10 protons, and 8 electrons is equal to hydrogen sulfide and 4 waters. So we are reducing sulfate here. These and other processes can serve as the half reaction that support the oxidation of organic carbon. The sequence of redox reaction that can occur as oxidants are depleted is shown in figure 16-1 and figure 27-24. In this figure, PE, or redox potential, a measure of electron potential or activity, determines when each half reaction can occur. Thus, only when oxygen is fully utilized will nitrate serve as an oxidizing agent, with denitrification occurring, followed by ammonifications. Subsequently, reduction of manganese dioxide, then ferric iron reduction to produce ferrous iron, and then sulfate reduction to produce sulfide can occur. Finally, carbon dioxide can be reduced to methane at extremely low PE values. The reduction half reaction are particularly important in the anaerobic hypolimnia of lakes. Within lake sediments and in wetlands that typically have very high organic matter content, trace metals are essentially important to cell metabolism because of their capacity for electron transfer during redox reaction and their affinity for protein complexation. Photochemical reactions. Unlike acid-base reaction and redox reactions that involve breaking covalent bonds to produce species with paired electrons, photochemical reactions typically result in the production of uncharged chemical species, each with a single free electron, that is, free radicals. Instead of both electrons in a covalent bond migrating to one of the two bonded atoms, a photochemical reaction results in a single electron on each atom. Photochemical reactions are initiated by the absorption of photons with sufficient energy to break a covalent bond that is at wavelengths mostly in the ultraviolet region, a process also referred to as photolysis. A chromophore is that part of the molecule where absorption occurs. Free radicals such as the hydroxyl radical as OH dot, not to be confused with the hydroxyl ion OH minus, are very reactive and rapidly undergo further reactions with other substances, which has implications for the chemical composition of natural waters close enough to the surface to be irradiated with wavelengths energetic enough to break bonds. Hydroxyl radicals can be produced via several mechanisms, including photolysis of hydrogen peroxide, ozone, nitrate, nitrite, dissolved organic matter, and the reaction of Fe2 with hydrogen peroxide called the photophanton reaction, when Fe2 plus and hydrogen peroxide are photochemically produced. A significant portion of chromophoric or colored dissolved organic matter degradation in surface waters occurs as a result of direct photochemical decay and reaction with photochemically produced hydroxyl radicals. This results in the gradual loss of chromophores and progressive degradation to smaller organic molecules and CO2. In boreal lakes, chromophoric DOM is dominated by humic and fulvic acids exported from wetlands. These compounds are relatively resistant to microbial respiration until irradiated. Photodegradation rates of chromophoric DOM are much higher than those of non-chromophoric DOM. Photochemical reactions are an important part of an abiotic pathway that transfers dissolved humic acids to particulate organic matter in sediments. The pH of the water has a very strong effect on photodecay rates of DOM, with low pH favoring rapid loss of DOM via enhanced production of hydroxyl radicals. The apparent mechanism for this is the iron-mediated photophanton pathway. Reoxidation of photochemically produced ferrous iron to ferric iron is rapid in circumneutral and alkaline waters, but acidic pH inhibits reoxidation, thus ensuring greater production of hydroxyl radicals. Complexation reactions. Complexes are chemical species that are composed of two or more entities that are capable of independent existence. There are two general types of complexes: ion pairs that are held together by the attraction of oppositely charged ions, for example, cadmium iodide, and then mercury Cl3, chloric, or coordination complexes where the main binding force is like a covalent bond with direct electron sharing between a ligand and an ion, usually a metal. Potential ligands. A ligand is an ion or molecule that binds to a metal atom to make a complex. Only require an electron pair that can be donated to the metal. Some common examples of ligands are water, hydroxide, NH3 and carboxylic acid, the carboxylic group. The later molecule is the acetate ion, where COO minus is shorthand for OCO minus. When water is the ligand, the process is called hydration. Organic ligands that have more than one site at which complexation to a metal ion occur are called multidentate ligands, and the complexes formed are called chelates. In natural waters, there are many dissolved substances, both inorganic and organic, that can act as ligands to form complexes. The DOM in natural waters, that is composed of humic and fulvic substances, is a very important group of ligands and has a critical role in the aquatic environment, affecting the bioavailability and toxicity of metals and other substances. Absorption, adsorption, and desorption reaction. Adsorption-desorption reactions are two-phase partition process, typically involving adsorption and is attachment of a solute adsorbate to the surface of a solid phase adsorbent. Desorption refers to the release of an adsorbed substance from an adsorbent. The solid phase can be settled sediments or suspended particulate matter, either live or dead or biological material, or inorganic suspended material. This process can be approximately described using a Freundlich isotherm equation of R is equal to Kf by CAQ of the power of 1 over n, where R is the ratio of the adsorbed solute to absorbent by weight. CAQ is the solute concentration, Kf is the Freundlich constant, Kf and n is an empirical value. Kf and n are coefficients specific for a given adsorbate and absorbent pair at a given temperature. As in the case of complexation reactions, adsorption-desorption reaction can affect the bioavailability of a substance and in some instances its toxicity. Factors regulating concentration of non-gaseous solutes. The concentration of a solute in the water column of a surface water at any point in time is the net result of dynamic processes defined as the difference between inputs from all sources and all outputs, including transport processes and chemical reactions. Inputs includes external inputs and internal inputs. Outputs include discharge through the outflow, sedimentation, degassing or volatilization to the atmosphere, microbial assimilation, and chemical reactions in the water column that consumed it. Not all inputs and outputs are applicable to every substance and every instance. For example, metals other than mercury do not have gaseous forms, and metals cannot be photodegraded. Furthermore, rates for a specific process can vary with location in a lake and time. This mass balance concept describing concentration as a function of inputs and outputs can be expressed with a simple differential equation of dCx over dt, where d is the inputs over dt, minus the outputs over dt divided by v, which is, I believe, v is probably the volume, is the lake volume. Cx is the mean concentration of a substance x at time t. Inputs and outputs are the instantaneous mass flux of x into and out of the lake at time t, and v is the lake volume. Over the time interval delta t, delta Cx is equal to delta inputs minus delta outputs divided by v. Well, delta means the difference over the time interval in equation 10.9 and 10.9a and 10.9b. Individual inputs and losses are implicit, but the equations form the conceptual basis of more complex deterministic models where separate inputs and output are explicitly described with process-specific formulae. Dynamic processes are the norms in lakes, but steady-state conditions can be assumed under some conditions, simplifying the model. Steady-state conditions assume that a lake is well mixed and has constant input and output rates, conditions which can be approximated in small lakes using mean concentration and fluxes average over a period that spans several years. At steady states, Cx is equal to inputs divided by V plus Q, where V is generalized loss coefficient that represents all potential net losses from the water column, and Q is a water discharge coefficient representing loss via the outflow. While equation 1010 works well for predicting long-term whole lake average concentration, it does not work well for predicting a whole lake concentration on a given day, week, or even a given year, because fluxes and biological process rates can be very dynamic. However, long-term averages smooth the short-term peaks and valleys, approximating a steady-state value. Okay, I think we are done for today, and we'll pick it up tomorrow on page 233 with equation 10-10. Thanks for attending today's introduction to chapter 10, and we'll see you tomorrow.